Continuity versus differentiability. The process for finding the derivative is called differentiation. A function is only differentiable at x if its derivative exists at x. As we have seen so far, a function's derivative does not always exist at any given x value. However, when a derivative does not exist at x, does that mean there is a discontinuity in that location, similar to when a limit at a point doesn't exist? Let's consider the function f of x is equal to the absolute value of the quantity x plus 2 at x equals negative 2. Well, we know that this function is continuous at x equals negative 2 because that's the vertex of this absolute value function. Let's find the derivative. To find the derivative of the function f of x is equal to the absolute value of the quantity x plus 2 at x equals negative 2, let's use the alternate form. However, since this is an absolute value function, to find its derivative, we will need to break it up into the following piecewise function, which is x plus 2 for x values greater than or equal to negative 2, and the negative of the quantity x plus 2 for x values less than negative 2. We know that the function evaluated at negative 2 will be equal to 0 because the absolute value of negative 2 plus 2 will be 0. From the right, using the alternate form, the derivative is the limit as x approaches negative 2 from the right of f of x minus f of negative 2 divided by the quantity x plus 2, which is equal to, or can be simplified to be, the limit as x approaches negative 2 from the right of x plus 2 minus 0 divided by x plus 2. Well, we can ignore the 0 because it's 0, and then x plus 2 divided by x plus 2 is indeed equal to 1. From the left, the derivative is the limit as x approaches negative 2 from the left of f of x minus f of negative 2 divided by the quantity x plus 2. And that simplifies to be the limit as x approaches negative 2 from the left of the negative of x plus 2 minus 0, all divided by the quantity x plus 2. Well, we know the 0, we can ignore it, and then we have the same factor, x plus 2, in both the numerator and denominator, so those can also cancel each other out, and we're left with negative 1 over positive 1, which equals negative 1. Well, as we can see, the right and left-handed limits or derivatives using the alternate form are not equal to one another. Therefore, f prime of negative 2 does not exist. Notice that the function f of x is equal to the absolute value of the quantity x plus 2 is continuous at x equals negative 2, and the limit as x approaches negative 2 does exist. However, the derivative f prime of x at x equals negative 2 does not exist. This is a crucial difference between a limit, a derivative, and continuity. Limits consider the value a function is approaching. As long as both the left and right-hand limits approach the same value, the limit exists. While derivatives are calculating the slope of the function as it approaches x from either side, which also needs to be the same. There are several instances where a function is continuous, but the derivative does not exist. We say that the function is not differentiable at the point where this occurs. A function fails to be differentiable if it has a corner, such as the absolute value function that we examined. For similar reasons, functions that have a cusp are also not differentiable at specific points. When there's discontinuity, the limit will not exist, therefore the function will not be differentiable. And the last case is a vertical tangent. If a function has a vertical tangent, it will fail to be differentiable. In the previous limits unit, we discussed what must be true for a function to be continuous. Remember, the definition of continuity states that, number one, f of c will exist. Number two, the limit of f of x as x approaches c will exist. And the limit of f of x as x approaches c will be equal to the function evaluated at c. As you have seen, differentiability requires the same criteria as well as needing a few others. In order for a function to be considered differentiable, it must also contain no discontinuities, no vertical tangent lines, no corners, and no cusps, and both corners and cusps are considered to be sharp points. Let's take a look at a diagram to understand this visually. We have this first oval of a Venn diagram, and this oval represents all functions that are continuous at x equals a, and notes the requirements necessary for this. So f of x is considered to be continuous at x equals a if f of a exists, the limit of f of x as x approaches a exists, and the function evaluated at a is equal to the limit of f of x as x approaches a. In other words, all of the requirements for continuity. This smaller oval represents the select functions that are continuous at x equals a and also meet the extra requirements to being differentiable, meaning f of x is differentiable at x equals a when there are no sharp points or vertical tangents. All functions that are differentiable are also continuous. If they're differentiable in here, they have to be continuous to begin with. However, continuity does not imply differentiability, because as we have seen, the absolute value function is one example of a continuous function that is not differentiable because it has a sharp point.